Nomine Patris et Filii et Spiritus Sancti. Amen. Veni Sancti Spiritus, Repletorum corde fidelium et tui amoris ne signim accende. Imiti Spiritum tuum et creabuntur, et redum vobis faciam terrae. Oremus Deus quid corde fidelium Sancti Spiritus illustratione docuisti, da nobis in eodum Spiritu recta sapere, Deus semper consolatione gaudere, per Christum Dominum nostrum. Ave Maria, gratia plena Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Santa Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. Sede sapientiae, ora pro nobis. Sancte Roberte, ora pro nobis. In nomine Patris et Filii et Spiritus Sancti. Amen. Okay, we're going to review how to simplify radicals. This is something that you will need to use in the next chapter for right triangles. There are certain triangles which have square root of 2 or square root of 3 involved in the ratios between their side lengths. So this does come up in geometry, and so we're going to do a quick review of how to do this, even though this is technically an algebra topic. So the radical, again, is just a word for this symbol. Okay, we call this the radical. Okay, or radical also means a root in a sense. Okay, something which is radical is at the root of some situation. So this is, as you know, this is the square root sign. Okay, this radical, just like this, where the index, okay, this number out here in front, we would call it the index, but right now there is none. That means it's actually 2. This is a square root. And what the radical does, its function is to undo squaring. It is the inverse function of squaring. So if I have something that's squared and I want to reverse that and get back to the original number that I had, I have to operate on this with the radical. So if I take the square root of something squared, that will cancel the squaring, it will undo the squaring, and we'll be back to the original value that we started with. Okay, so absolute value or plus or minus x. Okay, again, remember, it could be either plus or minus, because if I square a negative, I get a positive result as well. So we have to use the absolute value in a case like this. But there are other types of radicals as well, other than just the square root. I could have a cubed root, okay, or a fourth root, or a fifth root, or so on. Okay, so this number out here in front, it tells me which radical it is, or which operation I'm undoing with it, in other words, is called the index. Okay, but we are, in this class, in this course, we're going to mostly just be dealing with square roots. So we won't go into too much detail on these other situations. Okay, but if it's a third, all that means is you're undoing a cubing instead of a squaring. If it's a fourth power, then you're undoing something which was raised to the fourth power instead of a squaring, and so on. What's most important to remember when simplifying radicals is that this sign is kind of like it's a prison. Okay, it's prison bars. You cannot break out of this except if you have the key, and there's only one key to get outside of the radical, and that's you have to be squaring. You have to have something that is squared in order to destroy the radical, or in order to break this thing outside of it. And there are really no exceptions to that. The square root and the squaring are the only things which will undo each other. Okay, these are the keys which will operate on the doors of this prison to open or to shut it. So there is no other way to break something out of a radical. So, for example, when we want to simplify these, students will sometimes make mistakes with this because they forget this basic idea. This number 300 that's under the radical right now, no part of this, nothing in here can come outside of the radical or be freed from the radical or released unless it is something that is squared. And right now, 300 does not look like anything that is squared. Okay, but any number, okay, I'm not changing anything about a number if I break it into its factors. So we could think about numbers that when multiplied together will give us 300. So I could write 300 as 5 times 6, which would be 30 times 10, for example. Okay, so I could write 300 like this. This is still 300. I haven't changed anything, and I also haven't broken my rule. I have not released anything from the radical. Okay, there's no squarings in here, so nothing can be released yet. So this trying to factor it like this in order to simplify this radical doesn't really help me, because this is not really any simpler than just having 300 under the radical. So what I really want to do, if I can, is find factors of this number that are going to be in the form of perfect squares, because if something is squared, then I can free it from underneath the radical and maybe simplify this thing in some way. So, we see this most often like with perfect squares, where I have the square root of something that's already a perfect square. Like 64 is the square root of 8 times 8, okay, or square root of 8 squared. Here, the reason we can simplify square root of 64 to 8 is this is already a perfect square. This is 8 squared. So those things will cancel, and then that's the key that allows this to pass outside of the radical. So now I just have 8, and that radical got canceled on this. So with perfect squares, it's relatively easy. We recognize that, like 36 is 6 squared. 100 is 10 squared. But this is not different than this. This is not an exception to the rule that we already explained. Okay, this squaring is the only way in or out of this this radical. So if I can break this into factors that are perfect squares, that will be more helpful. So are there any factors of 300 which are already perfect squares? Well, I can think about my perfect squares. So my perfect squares are 4, 9, okay, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 64, 81, 100, and so on. Okay, so I want to know if there are any factors of this form, okay, of these perfect squares that will go into 300. The most obvious and largest one, and the one that will help us most quickly here, is 100. So I can write this as 100 times 3 would give me 300. So now I have something that's squared in here. Okay, 100 is 10 squared. And so what I can do is I can break this radical now into 2 parts. The 3 has to still remain under the square root, okay? It is not something squared. It has not been freed from the prison. But the 10 squared, it has the key to escape from this radical. I can cancel the radical here. Square root of 100 is 10. So square root of 300 can be written as 10 times the square root of 3. And this is not a perfect square of any whole number, let's say. So I can't break this out. This is trapped beneath the radical. It is not going to be freed here. Okay, this is the most that we can simplify this expression. You're not always going to be able to remove the radical entirely. You'll be left with square root of 3 or square root of 2 or square root of 5 or something in most cases. Are there other ways we could have simplified this? Well, yes, 300 is divisible by some other perfect squares as well. 4 and 25, for example. 300 can break into 25 times 12. Okay, 25 is 5 squared. So that becomes 5 square root of 12. Square root of 12 is divisible by 4 and 3. So I can actually simplify this further. 5 root 12 is root 4 times root 3. Root square root of 4 is 2, so 5 times 2 times root 3, so I get 10 root 3, and I get the same simplified result as I did using the other perfect square. So it's divisible by 25, it's divisible by 4, it's divisible by 100. There are different ways that you can break this one down into factors which are coming from perfect squares. Okay, let's look at a few more situations where we can simplify radicals in different ways. We'll start with this one because this is similar to the problem that we already worked. So if I want to simplify root 24, I need to think about factors that are perfect squares of 24. So I know that 24 is 4 times 6, for example. So square root of 24 can be written as square root of 4, which is a perfect square, times the square root of 6, which is not a perfect square. And I can then break that into two square roots multiplied by one another. They're both still under the square root sign. We have not freed this guy from prison yet, but this is 2 squared, so he has the key to get out of this. So square root of 4 is 2, but there is no perfect square here that I can really use, so that's as far as I can go. Okay, square root of 24 is the same thing as 2 times the square root of 6. If I have a square root of a fraction, well, that's the same thing as saying the square root of the numerator over the square root of the denominator. So if you see something like this, this is how you deal with it. You break it into separate square roots, one in the numerator, one in the denominator. So the square root of 1 is a perfect square, that's 1. The square root of 9 is a perfect square, that's 3. So we're allowed to eliminate both of these square roots, both of these radicals here. So we get 1/3. And if you think about this, this should make sense. Okay, if I were going opposite here, if I were squaring 1/3, I would have 1/3 times 1/3, which gives me 1/9, which gets us back to the original situation. So you can check these, just like with everything in algebra. If you do the inverse operation, you should get back to what you started with. Root 5 over root 3, well, this is a similar situation to what we had here, except the square root isn't over both of them at once. It's just 2 separate square roots. But that's exactly what we get when we broke this one down to the second step. So really, this is the same thing as if we had root 5/3, or 5 over 3. These, however, there are no perfect squares here. So I cannot simplify this numerator or this denominator as is. And there's a trick that we pull here. Hopefully you remember this trick. We do this thing called rationalizing the denominator. And rationalizing here means, well, we change the denominator into a rational number. In other words, not a square root. And to rationalize the denominator, remember, with fractions, I can always multiply the fraction by 1 and I don't change anything. And the way to get rid of a square root or radical is to have a squaring. So I need something squared down here in order to get the denominator to become a rational number. Well, if I had 3 times 3, then I would have 3 squared. So what we do is we multiply by 1 in the form of whatever this number is, okay, whatever this radical is here, we copy it, because then we'll have a squaring, and we multiply by 1 in that form, okay, of that number over itself. So in this case, root 3 over root 3. And when I multiply 3 times 3 down here, I get 9. Root 3 times root 3 is just, it's root 3 squared. Okay, and again, because these are inverses, the squaring cancels the square root. So we just get root 5 times root 3, which is root 15 over 3. And again, I want to simplify this if I can, but when I think about the factors of 15, none of them are perfect squares, so this is as simple as I can get this one. Let's actually add one more example like that. So let's say I have root 16 over root 7. Okay, the same trick I can pull here. Okay, if I square the 7, then I'm able to eliminate this radical. So I'm going to multiply this fraction by root 7 over itself. Then I get root 7 squared down here, which is just 7. And up top, 16 times 7 is going to be 112. But it's all under the radical, so root 112. Okay, now this I can simplify a little bit. Okay, if I think back about where this came from, I could have here taken root 16 and just simplified it to, since that's already a perfect square, simplified that to 4. So this is 4 times root 7. It's the same thing as root 112. Okay, or if we split this up, once we got here, we realize that this is 16 times 7, and that root 16 is a perfect square, which will reduce to 4. So we get 4 root 7 over 7 for the simplification of this. Now, this might not seem simpler than this original form that we had it in, but we have accomplished something which is useful here in algebra. We have moved this radical and gotten it out of the denominator, and that is actually helpful, believe it or not. Okay, a few other examples. If I have something that's already squared under the radical, okay, just like with these perfect squares, well, this is root 16 is root 4 squared. Well, then I already have what I need to free this. So these two operations are inverse, they cancel one another. So this is just going to be 13. If I have a more complex radical number, okay, with two parts, a whole number part and a radical part, and I square the whole thing, remember squaring is you multiply the whole thing by itself. So this means 2 root 3 times 2 root 3. Okay, it's not 2 times 3, it's 2 times 2 times root 3 times root 3. Okay, so this is like 4 multiplications going on here. 2 times 2 is 4. Okay, so you square the first number, and then I multiply that by root 3 times root 3, and root 3 times root 3, or root 3 squared, is just 3. So I get 4 from squaring this, and 3 from squaring this. So this is 4 times 3, which is just 12. 5 root 8, well, I can't do much with this except simplify this radical a little bit further. Root 8 is root 4 times 2, times root 2, excuse me. So this is 5 times 2 times root 2, or 10 root 2. So 5 root 8 simplifies to 10 root 2. We get as small of a number here under the radical as we can. Okay, and where you'll actually use this in the chapter is with right triangles, and here are some instances of something that looks like the Pythagorean theorem, which we've already talked about earlier in the year. So how do we deal with this? If we want to solve for x in this equation here, then we need to isolate x. Okay, we need to get it by itself. So 1 squared is 1, 3 squared is 9. I'll subtract 1 from both sides, and that leaves me with x squared equals 8. And to get x by itself here, we need to undo the squaring. And to undo squaring, we take the inverse. We use the radical, we use the square root. So square root of x squared is x, or actually it's the absolute value of x, technically, in algebra. We only use the absolute value here when we're dealing with variables like this, okay, not with perfect squares. You'll notice that when we had square root of 16 is equal to 4, we didn't say it's the absolute value of 4 or it's plus or minus 4. That's because with whole numbers, the square root is defined as the positive root and not the negative one. But when we're talking about variables, we don't know whether we're dealing with the positive or the negative root. So we do use the absolute value, or we do use this idea of x is going to be plus or minus something. So x here could be plus or minus the square root of 8. And again, when we simplified square root of 8 before, we got 2 root 2. So that's the same thing as 2 root 2. So x can be plus or minus 2 root 2 here. In geometry now, careful, because in geometry we're dealing with positive lengths and positive distances and things. So usually in geometry the negative is going to be left out because you're not going to have a negative length or side length of a triangle or something. But algebraically that's the solution here. Okay, last example. X squared is just x squared. 7 root 3 squared is this type of situation that we had here. So we square the first part of the term, 7 squared is 49, and we square the second part of the term, and we multiply those. Root 3 squared is 3. And then over here we square, again, we're going to square everything in here, which means this is 2x times 2x. 2 times 2 is 4. X times x is x squared. So this is 4x squared. Okay, and we want all the x's on one side. 49 times 3 is 147. We get x squared is 147 over 3. And again, we're going to take the square root. Okay, and again, if we can simplify this, we don't want this radical in the denominator. So we're going to multiply this by root 3 over root 3 to give us 441 over 3. 441, we need to check if this is divisible by any perfect squares. Okay, and after having done that and having thought about this for a bit, I realized, in fact, that this is 21 squared. I'll explain how I got to that in a moment. 21 squared equals 441. So square root of 441 is the square root of 21 squared, which just means that this is 21 over 3, which is 7. How did I figure out that 441 is 21 squared? Well, you could just go through and you could calculate all your squares until you find what this is divisible by. But also, if you think back to where this came from, this number, it was 147 times 3. And what 147 is 49 times 3. Well, 49 is 7 squared. 3 times 3 is 3 squared. And so we have 7 squared times 3 squared, which is the same thing as 21 squared. So if you can remember back to that, that's a shorter way of getting to this. The long way is just to go through and divide this by every perfect square starting with 4 until you find some that work. So this will also be divisible by 49. It'll be divisible by 9, I believe, and so on. Yeah, it's 49 times 9 is 441. So if you found those, then you can take the square root of those, get 7 times 3, which is 21, and you'll be here. You'll be golden. Okay, these are a few examples. The assignment I've given today is working with all of these types of problems to see how much you remember of this and whether you're still proficient at using these, because we are going to need to be able to do this for some of the problems in Chapter 8.